So you can paddle your kayak 6 miles per hour in still water. It takes you as long to paddle 15 miles upstream as it takes you to travel 21 miles downstream. Thank you. Determine the speed of the river's current. Okay, so it's kind of the same question, but it's different. Okay, well, how is it different? Because it says it takes you you paddle 15 miles upstream, but it takes you as long to travel 21 miles downstream. And when it says as long, where does it say that? Right here. It's talking about time right there, right? Because we have the distances. Now, we do know that it's 15 miles upstream and then 21 miles downstream. So naturally, you should be traveling further when you go downstream because the current is pushing you, right? Assuming that your paddling speed is consistent for those, however many hours this is. It looks like over 3. And if that's possible, that's great. I know I could go for maybe 5 minutes, but in any case, I'm anticipating this to be some kind of time application on this one, okay? And we know time is distance divided by the rate. But here's what I know is we do have upstream, right? So we're going to look at upstream. And we know that upstream is that's against the current, my bad. And then we got downstream, that's with the current, that's better. Okay, and again, what we see here, it says that it takes as long. That means in terms of the times, they're equal time. All right. Now, if I'm wrong on this, that's okay because we'll go back. But I'm expecting this to be time, right? So upstream, they did give us a distance. It took you 15 miles, or you were able to go 15 miles. That's our distance. The distance is the numerator. So you went 15 miles up the stream. That's against the stream. But they also say over here, hey, look, your paddling speed is 6 miles per hour. That would be if the water was completely still. So you're going to take your 6 miles per hour paddling speed, and it appears we're going to go against the current. So that's minus. Your speed is going to be less, so you're going to be taking away speed because the current's pushing against you. Now, I just put the variable c in there. Let's go ahead and define that, right? I'll do it this way. Hopefully it's easier. C is the speed of the current in miles per hour. Because everything right now, as far as I can see, is in miles per hour, okay? All right, and I think that's working. Let's look, though, at downstream. So downstream, it said you were able to go 21 miles. So for my ratio, my fraction, 21 is the numerator. Now your paddling speed, of course, in still water is the same, but now we're adding the speed of the current. And again, we expect it to be added because you were able to go farther in the same amount of time. That was kind of the point there. So these two ratios are equal. All right, to solve this one, of course, you could just make the denominators match, but this is a proportion right here. Now, what does that mean? It means that you could just use cross multiplication at this point. Okay, so I'm going to cross multiply these, it's going to keep them equal, okay? Now, if you wanted to, just take this side and multiply by 6 plus c, and then this side by 6 minus c, both numerators and denominators, you end up with the same thing on this, okay? So my green multiplication would be 15. Okay, so that's 15 times the, where it's crossed with multiplication, right? 6 plus c. And then on the right side, I'm multiplying, it's 21 times the 6 minus c. So I'm putting the 21 in front just so it looks kind of familiar there. But from here, we have some distribution, right? So we're going to distribute the 15. In my calculator, 15 times 6 is 90. 15 times c is just positive 15 c's. And this is equal to, let's distribute the 21. 21 times 6 is going to be 126. And then 21 times negative c is negative 21c. So I'm going to use a principle of equality at this point in order to kind of finish solving this. And I'm going to put the c's on the left and the numbers on the right. I don't really care if the coefficient's negative or not because we're going to divide. But that means the 90 is going to have to be zeroed out. So I'm going to have to subtract 90 from both sides. But in addition to that, I've got this negative 21c on the number side, so I'm going to have to zero that out as well. So plus 21c's on the right, but if I do it on the right, I got to do it on the left. So what does this do? Well, as planned, it zeroes out the 90 and the and the negative 21c's. Okay, but what do I get from the c's on the left? Well, I got 15c's plus 21c's is 36c's. This then equals 126 minus 90, which is 36. And then the last thing I need to do here is just make the coefficient of c a phantom 1. So it should read as c equals, and I'll do that by dividing 36 by itself. But if I do it to one side, I'll have to do it to the other side. Now this becomes a phantom 1 right there, but the other side, 36 divided by 36, I need to show that, okay? And this concludes the problem, because now we know what c is. C is 1. C, also at the top, we wrote that it represents the speed of the current. So the speed of the current is 1 mile per hour. Boom, that's it. Of course, if you're doing this on paper, you'd want to show 1 mph, and that's good too. Now, some students get to the point where they're like, yeah, Mr. Sal, that's great, but I really want to check. Well, check, okay? So remember, the times have to be the same, right? So the time for upstream would have been 15 divided by 6 minus 1. That's 15 divided by 5. That would have given us 3 time, right? So that's 3 hours upstream. Okay, we should get the same time for downstream. So 21 divided by 6 plus 1 is 21 divided by 7. It's 3 as well. So we put those back in and we checked, and we did find that it took the same amount of time for both. And again, that's using the time formula, distance divided by rate.